So this is number 56 on chapter 8. It states a uniform chain of length 8 meters initially lies stretched out on a horizontal table. A, assuming the coefficient of static friction between the chain and the table is 0.6, show that the chain will begin to slide off the table if at least 3 meters of it hangs over the edge of the table. B, determine the speed of the chain as the last link leaves the table, given that the coefficient of kinetic friction between the chain and the table is 0.4. So based on this problem, you're able to draw this diagram. So this will represent the table, and then you can tell that the chain, part of the chain is going to be on the table, while another part of it is going to be hanging off the table. So in part A, it states that show that it will begin to slide off when 3 meters of it hangs off. So what you can tell is that if 3 meters of it is hanging off over the edge of the table, that means that it will have maximum static friction from the table. So you want to, from that problem, you would have to try to gauge at how much of the chain could be hanging off the table. So from your given information, you know that the static friction of the table is 0.6, static kinetic friction of the table is 0.4, friction or static friction is equal to mu s Fn, and you want to find out an equation for Fn. Obviously, since the chain is going to moving, it's a non-constant amount. So you want to find like a representation of the equations. So you can see that you can represent the whole chain length to be L, and then you can say this part that's hanging off could be X, and then this would be L minus X, which equals a total of L. And L in this instance is going to be 8 meters. So you want to prove that X is going to be equal to 3 when it reaches maximum static friction. So first you can do sum of forces in the Y. You can tell that when you draw the forces here, the chain Fn is going to upwards, mg is downwards, and you can know that mg, or the mass, it's only L minus xm. So if you do Fn minus Fg of the force on the table equals 0, and you set them equal to each other, Fn is going to be equal to L minus x over L mg. This is the amount of the mass that's actually on the table. So you know this, and now you can go back, and this is going to be the force of the x direction. So when you have this force, there's going to be static friction that's pointing to the right, and then the force of the hanging part of the chain is going to be facing the other way. So you can do force of static friction minus the hanging force is going to be equal to 0. And you actually found out what Fn is from this part of the problem. So if you do mu s L minus xl over L mg, and then force of the hanging mass is actually going to be x over L mg, because this is the part of the chain that's going to be hanging off the mass. So it's going to be x over L mg, and you can just ignore the denominator. You just want the numerator to be equal to 0. So you do mu s L minus x equals 0, and you solve for x in this instance using algebra, and then you're going to find that x is going to be equal to mu s times L over mu s plus 1. And it gave you in the problem that mu s, or the coefficient of static friction, is 0.6. The total length of the chain is 8. And you divide that by this given expression right here. And what you find is that it's going to be 3/5 times 8 over 8/5, which is actually going to be equal to 3 meters. So therefore, you can assume that it is true that when the chain is hanging off by 3 meters, it's going to be right before it slips off. And then part B asks you determine the speed of the chain as last link leaves the table. So as it goes from 3 meters from the hanging and all of it comes off, like the third 3 meters is hanging and then all of it falls off, what's the speed of that? So what you know is that the equation is changing kinetic energy equals work net. And in this instance, the work net is going to be 2 works done. First is the work done by gravity, and obviously there's also work done by friction. And since it's taking away from the energy of the system, it's going to be negative. So you can take the integral of both sides. And the reason why you want to do the integral and not just force times delta x is because the x in this instance is going to be varying. So you take the integral from 3 to 8. 3 is your lower limit and 8 is your upper limit. And the work done by gravity in this instance is going to be x over L mg dx, given from this part right here. And then the work done by friction on this instance is going to be the integral of mu k in this instance, because the chain in this part is moving, over L minus x over L mg dx. And what you can do is you take out mg over L because they're constants, and then you have this expression right here. And then what you want to do is integrate it and take the antiderivative, because x to the 1, that's going to be half x squared. And then for this one, mu k times L is going to be mu k Lx, and then mu k times negative x is going to be mu k over 2x squared. And then you want to evaluate the integral, and after you do all these steps, you're going to get 45 over 16 mg. And that's not your answer, because what you did was just find the net work. And now, since you found the net work, you want to be able to set that to half mv squared. And you want to do half mv squared and not half mv final squared minus half mv initial squared, because it actually started from rest. So when you multiply by 2, divide by m, and square root it, you're going to be getting v equals 7.42 meters per second squared. And that will be your speed, as the last link, or the last part that's still on the table, is going to be leaving the table, and this is your speed.